Hmm. Hello, welcome class. Today we are going to start case study 4. I went ahead and outlined here in the beginning what are the 3 videos that I will be covering. Okay, we're going to start out with video 1. This is going to be an algebra review and introduction to correlation. Video 2 is going to be all about case study 4. We're going to get introduced to it and answer case study 4. And then video 3 is going to be some examples and practice. All right, so let's go ahead and get started with the algebra review. Okay, first thing about algebra review, okay, ordered pairs. Okay, ordered pairs, this is giving you the coordinate to an ordered pair on an x and y grid or x and y axis. Okay, so x is always the input or the independent variable, and y is always going to be the output. It's going to be the dependent variable. So y will always depend on what x is. Okay. Another important thing when we are talking about ordered pairs and lines is slope. Slope is the relationship between x and y. Okay, it can be expressed like this: the change in y over the change in x. Okay, something we're going to need to be using in case study 4 is these ideas with algebra review and lines. Okay, so a little reminder about slope-intercept form of a line. Okay, we have y equals mx plus b, where m is equal to the slope and b is going to be the y-intercept. Okay, so everything on this page right now is algebra related. You've probably seen it at some point in one of your previous classes. Okay, but now we're going to kind of transform that into statistics. Okay, so now we're looking down here in stats. Okay, in stats we have y equals beta naught. When the 0 is a subscript, we should say naught. So y equals beta naught plus beta 1x. Okay, this is the theoretical trend line and it's composed of parameters. The parameters specifically are beta naught and beta 1. I'm going to erase my comma. Beta naught and beta 1, those are our parameters for the theoretical trend line. Okay, then we have the line of best fit. That's going to be y hat equals beta naught hat plus beta 1 hat x. Okay, now the line of best fit is going to be composed of statistics. The statistics have the hat on top. Okay, so theoretical line is coming from the population. It's talking about parameters. We don't know them, okay? So that's just using what we know about parameters. Parameters always come from the population and we don't know them. So we're never going to be able to assign a value to those parameters, okay? Now the line of best fit, that's going to be a statistic. It's going to come from the information of the sample, okay? Beta naught hat, now I'm looking over here, beta naught hat and beta 1 hat, those are both statistics. So we will know what those are. Okay, so the line of best fit, so uses the sample to estimate beta naught and beta 1. So the line of best fit, that's what we called this. Okay, we use the sample to estimate beta naught and beta 1. Okay, just like in the past, we have used x bar to estimate mu. We're going to be doing that same thing here. Okay, what are we doing in case study 4? Okay, the goal of case study 4 is to use the data to create a model for prediction. Okay, in the past, we have built a confidence interval for a range of guesses on our parameter, or we've ran a hypothesis test in order to test a certain parameter. Now we're going to create a model in order to try and predict what can happen in the future. All right, using scatter plots to determine the relationship between x and y, okay? And we're gonna call that correlation. We'll get into correlation here on the next page. All right, correlation is the measure of the strength of the linear relationship between x and y, okay? I wanna emphasize the word linear here, okay? If it doesn't look like we have a linear relationship, then we shouldn't be talking about correlation. Correlation is very specific to a linear relationship between x and y. All right, there's two new symbols we need to know for correlation. R is the sample correlation coefficient. Okay, R is the sample correlation coefficient. So what do we know? R is a statistic. Okay, if it comes from the sample, it's a statistic. If it comes from the population, it's a parameter. All right, so we have this Greek letter rho. Rho is the population correlation coefficient, and I'm going to zoom in a little bit here. Rho is spelt R-H-O, and you kind of write it like that. Okay, I usually just kind of start at the bottom. Not quite like a P, a little bit differently. Okay, that's rho. And that stands for our population correlation coefficient. All right, another thing that we're going to need is regression. Regression helps us attain a line that best fits the data to use for our prediction. Okay, so to go back to my color pink, line of best fit. Okay, regression can help us attain a line that best fits the data. Okay, notice all my pink is talking about line of best fit or linear. Okay, that's important to relate and connect together. So regression can obtain a line of best fit to help fit the data to use for prediction. All right, and we're always using the data from the sample. So while now we're going to be predicting instead of testing, we still have that foundation of statistics where we use what we know about the sample to help us learn more about the bigger population. Okay, the last thing I have on this page is just kind of a list of these new symbols that we've just learned. Okay, a little further down. All right, so this box kind of got cut onto two separate pages. Okay, but we have this line for parameters. Okay, parameters come from the population, they're unknown, and then we have this line for statistics. Okay, so the slope, the parameter for the slope is beta 1. The statistic for the slope is beta 1 hat. Okay, it has the hat when it's going to be that estimate for us. Okay, the y-intercept parameter is beta naught. The y-intercept statistic is beta naught hat. Correlation coefficient, so that's what we talked about right up here, still visible on the screen. Correlation coefficient, we have the symbol rho for our parameter, okay? And we have the symbol R for our statistic of correlation coefficient. All right, so keep in mind parameters, they come from the population, they are unknown. We will never know what the parameter is unless we go out and sample the whole population, which we're not trying to do. So we're going to have statistics that are going to help us estimate these parameters. Beta 1 hat is going to help us estimate beta 1. Beta naught hat is going to help us estimate beta naught. R, that's going to help us estimate rho. Okay, so the next thing I want to get into is actually talking about correlation coefficient. Okay, so the sample correlation coefficient is R. All right, I kind of already mentioned before that the correlation coefficient measures the strength of the linear relationship. Okay, so again, linear relationship, that's an important part here. Okay. All right, so now just some facts about R. Okay, let's start at the first one. The smallest value for R is -1, and the largest value for R is +1. Okay, so then I wrote it right here. R can be anything between -1 and +1, inclusive, meaning it can also be -1 or +1. An R value equal to -1 indicates a perfect negative linear association. An R value near -1 indicates a strong negative linear association. An R value equal to 1 indicates perfect positive, okay? So notice -1 is perfect negative linear association. +1 is perfect positive linear association. Okay, and an R value near 1 indicates a strong. So notice it's not perfect, but it's still strong positive. An R value near 0 indicates little to no linear relationship between the two variables, okay? So if you get an R value near 0, okay, that's telling you, hey, there's not a linear relationship that's evident here. Okay, so what I want to do with these next few scatter plots is just kind of look at them and talk about what type of value or the words you would use for R here, okay? All right, so the dots represent the scatter plot, okay? That's the data that we went out and collected, all right? And the line that you see here, that's the line of best fit that we talked about over here, okay? It's the line of best fit, so what line best fits the data, okay? And the formula to get that line is a little complex, okay? It is doing multiple things to reduce, so like a good example is this line. The formula that was used to build this line you see right here was created to reduce the distance that each data point is away from the line, okay? It's making it to where that line is as close as it can get to every single data point that you see. Okay, I did mention that the formula is a little complex. We will not be worrying about the formula. More so, you need to know, well, what is this line telling me? Okay, so this line here, if we look at this first one, this line lies exactly on every single data point. Every single data point. Okay, so that is going to be either perfect negative or perfect positive. Okay, and the way we decide between negative and positive is the direction that we're going. Up and to the right is going to be positive relationship. Okay, if your data is going down and to the right, that's going to be indicative of a negative relationship. Okay, so what we see right here is a perfect positive relationship. And I can be confident that my R value is going to be equal to 1 precisely because every single data point falls on that line. Okay, let's look at the second one over here. So we know that it's still a positive relationship because it's going up and to the right, okay? Only this time, not every single data point is falling perfectly on the line, okay? So that means we're not going to have a perfect, I might even write that over here. This is perfect positive. The first one is perfect positive. The second one isn't going to be perfect positive. It's going to be strong positive. Okay, so that means the R value is going to be very close to 1, but not quite 1. So maybe around 0.9. Okay, that's close to 1, but not quite 1. Okay, and then if we go on and we look at this third picture, all right, so our line of best fit is still going up and to the right to give us an idea that, hey, this is a positive relationship. But notice only a couple of the dots come really close to that line of best fit. A lot of our dots of our data points, they're falling off that line. So that's going to be more indicative of a weak positive relationship. So this would be something closer to 0.4 or 0.5 range. Okay. And if we kind of reveal what they say, we see that, okay, we did get all of those correctly. Okay. So up and to the right is what we know for positive. Okay. When every single dot lies on that line, it's a perfect positive. We can be sure that R is 1. Okay, here we have a strong positive. We see a lot of the dots are touching the line and the rest of them are really clustered very closely to that line. So that's going to be strong positive. All right, and this third one, the dots are a lot more spread out. We still have a slight up and to the right, making it a positive linear correlation, but not very strong. We called it a weak positive. Okay. Now let's look at these. Okay, so we see that all of these are going down and to the right. So that's going to be that indicative of that negative relationship. Okay, so this fourth one, all right, all of those dots are lying perfectly on the line. So this is going to be an example of a perfect negative relationship. Okay, so perfect negative means R is going to be -1. Okay, here on this next picture, The fifth picture, okay, again, going down and to the right, we see that it's going to be negative, and the dots, again, they're clustered very, very closely to that line, but not every single dot lies on that line. So that means we should expect an R of around negative 0.9, okay? Negative because it's going down and to the right. All right, let's look at the sixth picture, okay? Our line of best fit that we see here in the middle is still going down and to the right, so we still have that negative relationship going on, but all the dots are scattered out and spread around now. So that means we're going to have that weak negative, and R would be around 0.4 or 0.5. Okay, weak negative linear correlation. The last picture that we have here, oh, it got cut off a little bit, but that's really all that we need to see. Notice that there is no line of best fit at all, okay? The dots are all scattered very randomly, and here we call this no linear correlation. Okay, so that means we should have an R value close to 0. No linear correlation at all here. Okay, so the next page, I have a few examples to go through and just, you know, label these graphs with words, and you can even kind of talk about the R value that you would expect to see. Okay, so this is the data. Notice the line of best fit isn't placed, but we can picture it, right? So here, these dots look like they're going on almost a very perfect straight line. Okay, and then the question then is that going to be perfect positive or perfect negative? Okay. The second one, all right, again, it looks like we have an almost perfectly straight line, okay? But now this line is going down and to the right, all right? So if I reveal this first one, that's going to be a perfect positive. That means we'll have an R value of 1. And the second picture to the right is a perfect negative, which means we'll have an R value of -1. All right. Let's look at these next two. Okay, so I don't think I can draw one line to perfectly fit all of them, but if you notice the line I'm kind of roughly drawing here fits most of them. They're very close, clustered together, going up and to the right. So that's going to be indicative of a strong positive relationship. All right, over here, down and to the right. And try that again. Okay, down and to the right, notice not every single dot lies perfectly on my line, but a lot of those dots consisting of our sample are very close. They're clustered around, but they're going down. So the first picture is of a strong positive relationship, and the second is of a strong negative relationship. Okay, so a strong positive means you would have an R value. I'm going to use the approximately around 0.9. Strong negative means it should be around -0.9, close to that. Okay, I can be positive up here because those dots, the scatter plot points from our sample, lie perfectly on the line. So when when the relationship is perfect, then I can be sure that it's either exactly 1 or exactly -1, depending on the way the data is going. All right, what about these last two? Okay, so trying to just, if I draw the best line that I can, notice I hit a couple of those points. That's really it. They're not nearly as close together as you see on the graph above. Okay, so we can call that either weak positive or moderate positive, or it's kind of just in the middle. Okay, now this second picture, you see, I can't really draw a good line to help represent what's going on here, okay? And look at the shape that you see. This should be kind of similar to something you've seen in algebra before. Looks kind of like a parabola, okay? It looks like a parabola, so that means that there isn't a linear relationship going on there. Oops, okay, so those are the words that go along with that. All right, so that picture up there, that's going to be the weak positive or moderate positive, okay? You might get an R value around 0.4, maybe, okay? No linear correlation is what we have going on up here. And that's going to be an R value of 0, okay? No linear correlation at all means we have an R value of 0. All right, and then just a little note here that linear correlation is discussed in section 14.4 of the textbook that you can find on my stat lab. Read section 14.4, but omit the subsection titled relationships between the correlation coefficient and the coefficient of determination. We will not be talking about the coefficient of determination in this course. Okay, so that is going to be the completion of my first video.